the last lecture in Module 5 on time integration techniques. In this lecture we shall focus on the application of the time integration schemes which we learnt in the previous lectures to unsteady transport problems. So let us have a recapitulation of what we did in the last lecture. We discussed multi-level methods for time integration of initial value problems. Then we looked at predicted character methods which included Runge-Kutta methods. We also looked at few methods which we can derive using finite difference approximation of the time derivative. Now let us apply a sample of these schemes to generic transport equation. So this is what we will focus on this lecture, application of time integration techniques to unsteady transport problems. So we will have a look at how do we apply the schemes which we learned for initial value problems for time integration of a generic transport equation. We will look at application of explicit methods to both diffusion problem and one-dimensional advection-diffusion problem. Their extension to multi-dimensional problems is fairly straightforward, and we will also outline the application of implicit methods to diffusion and advection-diffusion problems. Let us have a look at our generic transport equation for a generic scalar phi. So let us recall the governing differential equation which we had obtained for the transport of scalar phi. We had the time derivative term del of rho phi by del t plus this convective term divergence of rho v phi is equal to divergence of gamma times gradient of phi. This was our diffusive term plus the last term was our source term, that's q dot phi. Now what we can do is we can try and rewrite it in terms of fairly or in the form fairly similar to that of an initial value problems by keeping the time derivative on one side, transfer the remaining terms on the right hand side. That is to say, we will rewrite it as del rho phi by del t is equal to minus divergence of rho phi v plus divergence of gamma times gradient of phi plus q phi dot. Now this right hand side is basically our generic function f which we have introduced in the RHS of an initial value problem f t comma phi t. So on the left hand side we have got this time derivative, and on the right hand side we have got a function which depends on t and phi t. So now we can use any time integration scheme which we have learnt in the previous two lectures for integration of an initial value problem for this generic transport equation, and we have to be just careful how do we evaluate this f t phi t because it involves this these divergence terms. So they have to be evaluated at appropriate time step, and these derivatives ought to be replaced by corresponding finite difference approximations. Now if we use an explicit method, everything in the right hand side is evaluated only at times for which solution phi is already known, and if you use an implicit method, the discretized right hand side would involve values at new time level which would result in a system of algebraic equations which must be solved to obtain the solution at new time level. So now there is a trade off. If you want to use an explicit method, the evaluation per time step is very fast, but we have already learnt there is some stability considerations which limit the value of delta t which we can use. So whether we choose an explicit method or an implicit method, this would depend on the objective of our numerical simulation and the nature of the problem which would dictate the stability requirements. Let us elaborate these things further. Suppose we want to obtain a steady state solution, that is our primary objective. We have got an unsteady heat conduction problem or an advection-diffusion problem, but what we are ultimately interested in is obtaining what happens at t is equal to t infinity, that is to say what is the steady state solution. So now in this case, if we choose an explicit method, we would be forced to use small value of delta t because of stability considerations. So we will have to perform work computations for many time steps. So in such situation, implicit methods might be preferred which allow large delta t because there is no constraints imposed on delta t. Say suppose if we use an implicit backward Euler method, so we can use any pretty large value of time step and we can obtain the steady state fairly easily, though at each time step we have to solve a system of equations. So that is why in general if we have to obtain a steady state solution, that is the primary objective. In CFD we prefer implicit methods. On the other hand, if you want accurate time history, okay, then the choice of delta t would be dictated by the accuracy requirements. So as we know that smaller the delta t, more accurate would be our solution. So it may so happen that this accuracy requirements force us to take a delta t which is fairly small and it is small enough to meet the stability condition for an explicit method. So in this case it does not make much sense to solve a system of equation at each time step by choosing an implicit method. We should instead go by an explicit method, and this is one such case where for instance if you want to perform large eddy simulation or direct numerical simulation of turbulent flows, these require accurate time history, that we have to obtain our solution at each time step very accurately for velocity field as well as pressure field. So in such cases we prefer explicit methods of Adams-Basforth or Runge-Kutta family. Now let us have a look at application of explicit Euler method first to heat conduction, and then we will discuss its application to the advection-diffusion problem. We will also discuss briefly about the stability of different schemes, explicit schemes in particular. So unsteady heat conduction equations, suppose we assume that material properties are constant, that is we have got constant rho, Cp and thermal conductivity K. So in that case we can dump everything in our parameter which we call thermal diffusivity. So del capital T by del T, where capital T is our temperature, is equal to kappa times del to T by del x square. For the time being we have ignored the source term. If you want we can just put it, it does not really affect our time integration procedure or the stability of the scheme. So now for the sake of simplicity of the formula we have just noted down the case where there is no source term. Note down here that kappa is thermal diffusivity. Now let us use our explicit Euler method. So T capital T n plus 1 is equal to capital T n plus kappa times delta T del 2 phi over del x square. Now this derivative has to be evaluated at the known time instant, and now we should choose an appropriate finite difference approximation to this second order derivative with a spatial coordinate x. So suppose we choose central difference scheme which is called CDS for the diffusion term, that is del to T over del x square. So the resulting scheme is popularly called FTCS, forward time central space. So this is shortened notation, this forward Euler time and central difference scheme in space. And if you have chosen a uniform grid, then the discrete equation is simply this T I n plus 1 is equal to T I n plus kappa times delta T. The terms in the brackets, big bracket, T I plus 1 n plus T I minus 1 at n minus 2 T I n divided by delta x square. This is our central difference approximation for the second order derivative in time. And note down this particular scheme, it is first order accurate in time. Its truncation error would be a first order because we have used forward Euler method which is first order accurate in time, and we have used central difference approximation in space. So this is why its accuracy or the truncation error in space would be of the order delta x square. So this FTCS scheme, it is first order accurate in time and second order accurate in space. Now let us introduce a non-dimensional number which we would call diffusion number d to simplify our expressions. So d is kappa delta t divided by delta x square. We can rewrite it as delta t divided by delta x square by k. So on the numerator what we got, this is our time step, and this delta x square by k, this would again give us a time scale. Okay. So now this particular time scale, it gives us what we call characteristic diffusion time, that is the time which would be required for transmission of a disturbance by diffusion. So, this diffusion number d is the ratio of time step to the characteristic diffusion time. So, now in terms of this non-dimensional parameter, our algorithm can be written in a very simple form. So, explicit FTCS algorithm for 1D heat conduction equation can be written as Ti n plus 1 is equal to 1 minus 2D Ti at n plus d times T of I plus 1 n plus d times T at the grid point I minus 1 evaluated at time level n. Now, let us see this stability of this algorithm. We have already seen the accuracy aspect. Now, stability conditions can be obtained with von Neumann method or by requiring the coefficients of all nodal values must be positive. Now, this is a physical requirement. If you look at this formula on the right hand side, we have got 1 minus 2d, this is the coefficient of Tin. The remaining ones Ti plus 1 and Ti minus 1, their coefficient is d, which is a positive number. Now, if you want a similar sort of contribution from all the 3 nodes at a future time instant, the contribution coming from each grid point I plus 1 and I minus 1, that should be positive, otherwise that might lead to oscillations or instability in the solution. So, this is one of the requirements or one of the ways in which we can look at or measure the stability of an explicit scheme would be to look at the coefficient of each term and require that each coefficient must be positive. Now, let us try and derive this stability condition using both the approaches. First, let us have a look at this von Neumann approach. So, von Neumann stability analysis. Now, this von Neumann stability analysis is basically related to the local solution, that we are looking at a solution in the vicinity of a particular node, and what we can do is this local solution can be expressed in terms of complex eigenvectors. So, that is the assumption which is made in this von Neumann stability analysis. So, local solution can be expressed let us call it as T j at n sigma to the power n, where sigma is a scalar quantity, e to the power the straight I alpha j. Now, this straight I which we have put not in italics I, this I is our imaginary number minus root 1, the square root of minus 1, this is what we call is our imaginary number. Alpha is what is known as wave number. Okay, so now in terms of this Tj n, the way we have defined it, let us write down our explicit scheme, this FTCS scheme which I have written earlier. FTCS scheme for heat conduction. So, we said Tj at n plus 1, this was given by 1 minus 2d Tjn plus d times Tj minus 1 n plus Tj plus 1 n. So, let us substitute in the terms of this complex eigenvector for all these variables Tj. Now, Tj n plus 1 would become, on the left hand side we will have sigma n plus 1 e to the power I alpha j, where I is our complex number On the right hand side we will get 1 minus 2d times sigma to the power n e to the power I alpha j plus d times sigma to the power n e to the power I alpha j minus 1 plus sigma to the power n e to the power I alpha j plus 1. Now, let us divide this equation, both sides of this equation, 3, divide 3 by sigma to the power n e to the power I alpha j. So, what we are left on the right left hand side is sigma. Sigma is equal to 1 minus 2d plus d times e to the power minus I alpha plus e to the power I alpha. Now, e to the power minus I alpha and e to the power I alpha, they can be expanded in terms of sine and cos. So, this would become 1 minus 2d plus d times cos alpha minus I sin alpha plus cos alpha plus I sin alpha. So, now let us collect the terms. So, 1 minus 2d plus twice of d cos alpha. The imaginary terms, they cancel out, or let us rearrange it as sigma is equal to 1 minus 2d 1 minus cos alpha. Now, if we want our solution to be stable, we would require that the magnitude of sigma should be less than 1. So, stability requires that magnitude of sigma should be less than 1. So, we get two possibilities, that is your minus 1 should be less than 1 minus 2d into 1 minus cos alpha, and this should be less than 1. So, these two inequalities, let us take one by one. Let us take the first right inequality. So, 1 minus twice of d 1 minus cos alpha is less than 1. If we subtract it, subtract 1 from both the sides, this will lead to minus 2d into 1 minus cos alpha, this should be less than 0, divided by minus 2d. So, this inequality changes and we get 1 minus cos alpha should be greater than 0. Rather, we have got this equal to signs here. Now, remember cos alpha is always less than 1 in magnitude. So, this holds, this inequality holds for any alpha. So, this did not give us any requirement. So, now let us have a look at the second half of the inequality. It is minus 1 is less than or equal to 1 minus 2d 1 minus cos alpha. Let us add 1 on both the sides of the inequality. So, we get 0 is less than or equal to 2 minus 2d 1 minus cos alpha now this tells us this 2 is greater than or equal to twice of d 1 minus cos alpha or we get d should be less than or equal to 1 over 1 minus cos alpha. Now, what is the maximum value of cos 1 minus cos alpha? Minimum value of cos alpha is minus 1. So, this maximum value of 1 minus cos alpha, this would become 2. So, therefore, this inequality says that d should be less than or equal to half. So, this is the stability requirement which we get from von Neumann analysis, that is to say our diffusion number should be less than half, which puts a restriction on the time step. Okay, now let us have a look at a few more consequences of this requirement. Let us note down that d was given in terms of delta t divided by delta x square by k. Now, for stability we want d to be less than or equal to half. So, we have chosen 1 delta t for our time integration, and suppose in some regions we want to refine our spatial mesh. So, if spatial mesh, so if spatial mesh is refined by a factor of half, the definition of d and this requirement says that the time step must be reduced by a factor of 4, that is our new delta t prime, that should be delta t by 4. So, now that is a severe restriction, and that is the reason why this explicit Euler method is not suitable for the problems for which we would like to reach this steady state quickly. This particular method we are going to retain or use only for the cases where we require very accurate value of temperature at each time step, that is to say if we want a very accurate time history. Now, remember this particular condition which we derived from von Neumann stability analysis, we could have also derived it earlier by let us seeing the coefficients in this FTCS algorithm what were the coefficients. Let us have a relook at Ti at n plus 1 was 1 minus 2d Ti n plus d times Ti minus 1 n plus d times Ti plus 1 n. Now, the last two they are anyway positive. Stability requires that the first coefficient must be positive, that is our 1 minus 2d should be greater than 0, and which straightway leads to the same condition that d should be less than or equal to half. So, whether we perform the von Neumann stability analysis or we impose the restriction of all the coefficients for all time values of the function, this should be positive, they lead us to the same stability condition. You can say this FTCS algorithm applied to the heat conduction problem, the stability requirement is the diffusion number d should be less than half. Now let us apply our explicit equation Euler method to Advection-diffusion problem. So 1D Advection-diffusion problem, we have already seen its generic transport equation and written in terms or in a form very similar to an initial value problem, where we would assume the velocity to be constant and fluid properties also to be constant and no source term. So we will write it as del phi by del t is equal to minus u del phi by del x plus gamma by rho del 2 phi over del x square. So this is in a form very similar to our standard initial value problem. So our d phi by dt, and the right hand side this is our function f. So let us apply explicit Euler methods. We get phi n plus 1 is equal to phi n delta t times this function evaluated at Tn, that is minus u del phi by dx plus gamma by rho del 2 phi over del x square at time instant n. Now we have got two derivatives here, one with the convection term del phi by del x and one with the diffusion term del 2 phi by del x square, and at each grid point we need to find out their finite difference approximation. So now let us say we choose a uniform grid and we use central difference scheme for all spatial derivatives. That will again lead to what we call FTCS scheme. So the discrete equation for the value of phi at node I is phi I n plus 1 is phi I n plus delta t minus u times phi I plus 1 n minus phi I minus 1 n divided by 2 delta x. This is a central difference approximation for our del phi by del x term plus gamma by rho. Next we have got the central difference approximation for del 2 phi by del x square term, that is phi I plus 1 n plus phi I minus 1 n minus 2 phi I n divided by delta x square. To write this equation more compactly, let us introduce few numbers or two non-dimensional parameters. So let us define non-dimensional parameters c and d as c is defined as u delta t by delta x. If you rearrange this definition, it is delta t by delta x by u, and d is defined as gamma delta t divided by rho times delta x square, which can also be written as delta t by rho delta x square by gamma, which is equivalent to our diffusion number which we have seen earlier in the context of conduction problem. So this parameter d is nothing but diffusion number which we have seen earlier. Now let us have a look at this parameter c. Now the c is called Courant number because it was introduced by Courant first, and it is ratio of what? It is the ratio of time step delta t. Now this, what is delta x by u? This delta x by u tells us the time which will take for a disturbance to traverse distance delta x. So that is why we call it as convection time. So Courant number becomes now the ratio of the time step to the convection time. Now in terms of these two parameters c and d, this is the shorthand form of explicit FTCS algorithm for Advection-diffusion problem. Phi I n plus 1 is equal to 1 minus 2d phi I n plus d minus c by 2 phi I plus 1 n plus d plus c by 2 phi I minus 1 n. Now we want to look at the stability of this method. So this again can be obtained by either using von Neumann analysis which we have done earlier, or by requiring the coefficient of all nodal values must be positive. Now let us try this approach, the second approach, for deciding on the stability of this method. So our FTCS algorithm for Advection-diffusion problem. So what we had is phi I n plus 1, this was given as 1 minus two d phi I n plus d minus c by 2 phi I plus 1 n plus d plus c by 2 phi f I minus 1 n. We want all coefficients on the right hand side to be positive. So, for stability, coefficients of phi I n, phi I plus 1 n and phi I minus 1 n must be positive. That is 1 minus 2d should be greater than or equal to 0, d minus c by 2 should be greater than or equal to 0 and d plus c by 2 is greater than or equal to 0. The last one is obvious, d and c were both positive numbers. So, this holds good since d and c are positive. So, basically we have got these two conditions. So, thus the stability requires, the first one says that 1 minus 2d should be greater than or equal to 0, that is d should be less than or equal to half. This was the same requirement which we had earlier derived for the case of heat conduction equation, and this is the one which is going to put a restriction on time step. Okay. And the next one is says d minus c by 2 should be greater than or equal to 0. That translates to what we call a restriction on our velocity field, or it leads to the local self-Peclet number. This should be less than or equal to 2. So, the first condition or first requirement puts a limitation on time step, the second one puts a limitation on our spatial discretization. Now, let us have a look at one more case. If d is equal to 0, then what will happen? If d were equal to 0, this first coefficient 1 minus 2d, that will be positive, but what happens to the second one? The second coefficient will always be negative. So, that means for no diffusion, this FTCS algorithm for advection-diffusion problem is unconditionally unstable, and with diffusion we have already derived the conditions that d should be less than half and d should be greater than c by 2, which tells us that local Peclet number should be less than 2. Now, can we improve upon these situations, specifically when diffusion is very small, that is convection dominated problem? We would like to have an explicit scheme which has got better stability property. So, improved stability can be obtained with what we call upwind difference approximation of convective term. For diffusive term we would still continue to use our center difference approximation, but when it comes to the convective term, let us use a upwind difference scheme. So, if we assume u to be greater than 0, that is flow is from left to right in x direction. So, upwind difference approximation for del phi by del x would be phi of I minus phi of I minus 1 divided by this 2 shouldn't be there, this would be phi I n minus phi I minus 1 n divided by delta x, this factor of 2 should be missing there, plus gamma by rho, the second term is a central difference approximation for del 2 phi by del x square. So, phi I plus 1 n plus phi I minus 1 n minus 2 phi of n divided by delta x square. Now, if you introduce our earlier terms diffusion number and the Courant number, so in terms of that c and d parameters, this particular algorithm which we called upwind FTUD CS scheme, it becomes phi I plus 1 is equal to 1 minus 2d minus c phi I at n plus d times phi of I plus 1 n plus d plus c times phi of I minus 1 n. So now what we can easily say here, the coefficients of phi I plus 1 and phi I minus 1, they would always be positive. So there is no restriction whatsoever in terms of local self-Becquerel number, and the first one, this is the one which we should require to be greater than 0 for the sake of stability. This will put a restriction on our time step, and if you put that, this is what we get. So stability requirement simply say this, so delta t should be less than 1 by within big brackets 2 gamma divided by rho delta x square plus u by delta x. And we can easily see that if this no diffusion d is equal to 0, then this particular criteria would lead us to what we call the Courant number should be less than 1. Okay, because this first term is less than, sorry, this first term becomes 0, so we straightway get this particular restriction. Now this condition is also referred to as Courant-Friedrichs-Lewy condition or the Courant condition, and this is an important requirement for the use of explicit time stepping schemes in CFD applications, that the Courant number should always be less than unity. Now let us move on to some implicit methods, and let us apply our backward Euler method to the two problems which we have discussed. So first, application of implicit Euler method with central difference scheme for a spatial derivative for our heat conduction equation. So we had Ti n plus 1 is equal to Ti n plus kappa times delta t, Ti plus 1 n plus 1 plus Ti minus 1 n plus 1 minus 2 Ti n plus 1 divided by delta x square. Introduce our diffusion number. In terms of diffusion number, this algorithm could be written in simpler form: 1 plus 2d Ti n plus 1 minus d Ti plus 1 n plus 1 minus d times T of I minus 1 at n plus 1 is equal to Ti n. So now this is an equation which has to be solved. Not just Ti at n plus 1 is unknown, Ti plus 1 at n plus 1 and Ti minus 1 at n plus 1 are also unknown. So we will collect such values at all the nodes and we will get a system of linear algebraic equations which must be solved at each time step to obtain our solution. In the same way, we could have also applied our Crank-Nicolson method and we would have obtained an algorithm which looks fairly similar to this. Next, if you apply implicit method with the CDS for advection-diffusion problem, here we have used the CDS for this convective term as well as diffusive term. So phi I n plus 1 becomes phi I n plus delta t minus u times phi I plus 1 at n plus 1 minus phi I minus 1 at n plus 1 divided by 2 delta x plus gamma by rho phi I plus 1 n plus 1 plus phi of I minus 1 n plus 1 minus 2 phi I n plus 1 divided by delta x square, or in terms of diffusion number and Courant number, and rearranging the terms we get 1 plus 2d phi I n plus 1 plus minus d plus c by 2 phi I plus 1 n plus 1 minus d minus c by 2 phi I minus 1 n plus 1 is equal to phi I n. So this again a coupled system of equations. This is what we will get if you collect this equation for all the nodes, which would again be a linear equation. So we ought to solve a system of linear equations to get our solution while using our implicit Euler method. So now let us summarize the disadvantage which we will get, that requires solution of a set of equations at each time step, and please remember our implicit Euler method was first order accurate in time. So that is it, and the disadvantage which we have got this with this method. Of course, if you want higher order accuracy, we can move on to the Crank-Nicolson method or higher order Adams-Moulton method in time. Now as far as implicit Euler method is concerned, it has also got a very big advantage, that this method is unconditionally stable for any choice of delta t. So it allows use of a large time step, and thus it is very useful for solving steady flow problems, whether we are dealing with a steady, our aim is to obtain a steady state solution of a heat conduction equation, or an Advection-diffusion equation or a full Navier-Stokes equation, we can use implicit Euler method to quickly obtain, using large time step values, our steady state solution. So that is the big advantage which our implicit Euler method provides. Its stability properties are so good that this is the preferred choice for solution of non-linear time dependent equations. So that is where we would stop as far as the applications are concerned. For more applications and results, please refer to the books which we have discussed earlier, like Chung's book on computational fluid dynamics. It contains many algorithms, their stability analysis and so on. Similarly, you can also look at the book by Fursiger and Perek, which gives further detailed applications of time integration schemes to Advection-diffusion problem with some examples. And for looking at various time integration schemes which you can extend to our heat conduction or Advection-diffusion equation, you can look at the book by Wood.